Today, we're going to continue finding more derivatives of functions. Remember, this setup is that we have a bunch of core derivatives, some base derivatives that we need to remember, and then we are going to combine them with these three rules. So the product rule, quotient rule, and chain rule for products, quotients, and compositions of functions. The more derivatives that we put over here in our core derivatives list, the more derivatives we can take using these rules. The nice thing about differentiation, that's the process of finding derivatives. The nice thing about finding derivatives is that once you have these three rules, you're pretty much done. We just keep adding to the list of core derivatives. We look how they're combined with these three rules, and these three rules will get you through everything. One of the things that happens in math class is that you have to learn a process backwards and forwards. So we learn to take derivatives, then we have to do integral calculus where we learn to find antiderivatives. We go the other way. So that would be given nx to the n minus 1, we figure out how to find x to the n. The strange thing about this derivative process is that it doesn't really work so cleanly in reverse. It's so nice and straightforward. We got these three rules. Everything fits into one of these three rules. We just have to figure out what our basic derivatives are. With integration, it's not so simple. We can't just have an anti-product rule and an anti-quotient rule and an anti-chain rule. We do have an anti-product rule. We do have an anti-chain rule, but then there's a bunch of functions that don't even fit this description, where we can't use some process for finding the antiderivative. So it's a little bit strange to do things that way, or it's a little bit strange that things worked out that way. So today we're just going to add some more items to our list of core derivatives. But before we do that, let's remind ourselves of what these derivatives are telling us about. I have a problem from the second part. Turn this on. We have here a problem from part 2 of the chapter 3, section 2 homework. This is problem 3 on chapter 3, section 2, part 2, which is all about local linearization or linear approximations. We want to try to solve this equation at e to the 3x plus x equals 2, and we're told that it has a solution near x equals 0. The problem is we don't have some algebraic technique to get us at x. We can't just easily do some stuff to both sides of the equation and solve for x. Part of it is we've got this e to the x function, this exponential function mixed with this polynomial function x. And so there's not going to be a way to resolve this. So we find and do the next best thing and find an approximation of the solution. The instructions tell us exactly what to do. Replace the left side with a linearization to approximate the solution. So what we're going to do is find the tangent line approximation to e to the 3x and use that to solve the equation. So our strategy is to find the equation of the line tangent to e to the 3x. Let's find the equation of the line tangent to e to the 3x near x equals 0. So to find the equation of a line, we need a point and a slope. For the point, I'll just plug 0 into e to the 3x. So the point we're going to use is 0, 1. When x is 0, e to the 3x is equal to 1. So the point that we're going to have is 0, 1. The slope of the line is going to be the derivative of the function. So if our function f of x is e to the 3x, then f prime of x is e to the 3x times the derivative of the inside using the chain rule, 3. The slope of the line will be the derivative evaluated at 0. So that'll be 3e to the 3 times 0, which is 3. So now I have a point, 0, 1, and a slope, 3. And we put those together. So that means near 0, e to the 3x is approximately equal to 1, 0. So I'm going to use the slope intercept form since I have the intercept. 1 plus 3x. E to the 3x is approximately equal to 1 plus 3x near 0. Further away from 0, the approximation gets worse. But near 0, this is a good approximation. Near 0, this is the best linear approximation. So I'm going to replace e to the 3x in the equation with 1 plus 3x. So e to the 3x plus x equals 2 becomes the equation 1 plus 3x plus x equals 2. So our solution is 1/4. Any questions?
Yes, Professor Rich.
Yes.
When you write down near x equals 0, then e to the power 3x, how do you get approximately 1 plus 3x? Can
1
you?
plus 3x is the line tangent to e to the 3x near x equals 0.
Oh, where the 1 coming from?
1 comes from the point 1, 0.
And then the 3x,
0, 1.
the 3x is the 3, and then you put the x like a formula.
Y equals mx plus b.
Okay, so the 3 is right there, right? Correct?
Yeah, the 3 is the slope.
And then could you repeat the second line after that, e3x plus x?
So this is the equation we're trying to solve. E to the 3x plus x equals 2.
Yes. Right.
We're replacing e to the 3x with the approximation of e to the 3x.
And how do you get 1/4?
I solved this equation. 1 plus 4x equals 2. I subtracted 1 from both sides, divided by 4.
Okay, that's help. I'll look it up later. Thanks, Professor Rich.
Professor?
Yeah.
Can you just like quickly explain how you get the derivative for the e to the x with the constant?
Yeah. So we have the derivative of e to the 3x. The 3x is an inside function, so we're using the chain rule.
Mhm.
So let's see, separate out. So we're looking at f of x is e to the 3x. 3x is the inside function. So I'm saying u equals 3x. When we read the function to see what's going on, the first thing that happens to x is that it gets multiplied by 3, and then the result is plugged into the e to the x function. So we have a composition of functions. First, we do this 3x, and then the y function from the chain rule is e to the u. So the derivative of e to the u is e to the u times the derivative of u. So f prime, the derivative of e to the u is e to the u, and u is 3x, times the derivative of the 3x. So if u is equal to 3x, then du dx is 3.
Got it. Thank you.
It's a good color set for October. You can't see this, but the 3 is in purple, and I got the green and the orange. So good color set for October. I know we're only halfway through September, but if we take a look at the function e to the 3x and the tangent line 1 plus 3x near x equals 0, we can see that the line approximate is very close to the e to the 3x near 0. Then e to the 3x does its horizontal asymptote thing, and y equals 1 plus 3x does its linear function thing. But the closer we look, the more the line resembles the exponential function. This is important because if we try to solve if we look at the equation e to the 3x, and then we add x to it, let me turn these two off. If we look at the function e to the 3x, we're told that there's a solution near 0. So I'm going to graph the function y equals e to the 3x and the function y equals 2. We know that there's a solution near 0. So I approximate e to the 3x plus x with its linear approximation to find the point of intersection. So what we used was, instead of e to the 3x, I replaced the e to the 3x with 1 plus 3x, the tangent line, plus x, plus x. And so the actual solution that we're looking for is the 0.197. But the solution that we found was 0.25. So our solution was a little bit off because we were using an approximation of e to the 3x, not exactly e to the 3x. Now keep in mind, this problem is not about solving the equation. This problem is about understanding how linear approximations work. Because as you can see, I have a better solution to the equation just by looking at a picture, just by opening up a browser and opening up a free site on that browser and looking at a picture. If I wanted even more, then I could always just grab Wolfram Alpha and ask Wolfram Alpha about the equation. Oh, but it won't read it correctly because it's reading it correctly. Sorry, Wolfram Alpha, I forgot. So there's our e to the 3x plus x equals 2. And oh, standard time, computation time has exceeded. Sometimes when that happens, if you just reload, then it'll redo it. Oh, no. Here's the fun parts. Let's see. Oh, there we go. Approximate form. There we go. Now we have more decimal places. Here's the fun parts where you go the exact form and you'll copy this down exactly. And I'll say, what's the function W? And it's very obvious. Like I said, a lot of times it's very obvious when you're just going to use Wolfram Alpha to solve your problems.
Professor Lish, I have a quick question, please.
Yes.
On this problem, on the decimal and the Wolf alpha, the answer is x1/4 is 0.125, and it shows the line is, the y is 2. Once we get the 1/4, then we can plug back the original, we can also get 2, right? Am I right?
We'll get approximately 2.
Oh, okay.
Because we're not getting the exact solution, because we're approximating e to the 3x with a line. So we saw that our solution was a little bit off the actual solution. If we try to plug it back in, if I go e to the 3 times 1/4 plus 1/4, we're off of 2 by a little bit. We're at 2.36.
But on decimal, it showed 2, right? Correct? On decimal, the line is at 2.
The line was at 2.
But if we get 1/4, we plug back to the original, we get 2.36. Is that what you're trying to say?
That's what I'm saying, yes.
Oh, got it. Thank you.
Which is not quite 2, but we use we're approximating the solution, not getting the exact solution.
Got it. Thank you.
All right, let's look at a new derivative for the day. So we want to write a new core derivative. Here's the important parts of the day. The derivative of natural log of x is 1/x. The derivative of natural log of x is 1/x. This is your new core. That's going to be the only one. This is the last core derivative, new core derivative for this week. We didn't talk about how to find this derivative. This is just something I need you to know. The derivative of natural log of x is 1/x. We need to know how to use the derivative of natural log of x is 1/x with all of our rules: product rule, quotient rule, and chain rule. So let's do that. Let's say, for example, we want to find the derivative. Oh, let's say f of x. I was using function notation. Let's say the f of x is the natural log of x squared minus 3x minus 4. In this problem, in this function, we think about what we do with x. X gets squared, we subtract 3x and then subtract 4, and then take the result of that and run it through natural log. So we have a composition of functions where we start off with x squared minus 3x minus 4. So this is going to be our inside. This is u. That means our y function, the outside function, will be the natural log. So y is natural log of u. So we're going to take the derivative of y with respect to u and then multiply by the derivative of u with respect to x. So we're also going to need the du dx which will be 2x minus 3. So we're using the chain rule. F prime of x, we take the derivative of y with respect to u. The derivative of natural log of u is 1 over u. Times the derivative of u with respect to x, which is 2x minus 3. We wouldn't write it in this crazy separated fraction, but I wanted to make sure that we separate out the 1 over u times the derivative of u. We would more properly write this as just one fraction, 2x minus 3 over x squared minus 3x minus 4. We should always try to simplify our rational expressions, but 2x minus 3 is definitely not a factor of x squared minus 3x minus 4. So I'm not going to worry about factoring x squared minus 3x minus 4. Now, if we do the same thing that we did yesterday, and I just start moving things around, let's suppose that g of x is x squared minus 3x minus 4 times the natural log of x. Now, when we think about what happens to x in this problem, first, x gets squared, we subtract 3 times x, then subtract 4, and hold that result to the side while we take x into the other part of the function, find the natural log, and then multiply the two results. So this tells us that we're doing a product rule. So I'm going to say that I'm going to identify a first and a second, and then use the product rule. So the first will be x squared minus 3x minus 4, and the second will be the natural log of x. The derivative of the first is 2x minus 3, and the derivative of the second is 1 over x. Using our new shiny core derivative. So, using the product rule. The product rule says take the derivative of the first times the second plus the first times the derivative of the second This would be perfectly acceptable. If I was reading, if you wrote this down as your answer and just left it at this and moved on, that would be perfectly acceptable because I can clearly see the derivative of the first times the second plus the first times the derivative of the second. I would be totally happy with this answer. Computer might disagree with me, but you know, computers are dumb. Look how much effort we have to put in to just teach computers what a stoplight is. Now, this first factor, 2x minus, this first term has two factors, this polynomial 2x minus 3 and a natural log of x. So I won't be able to combine up my polynomials because I don't have polynomials. I got natural log of x times the polynomial, then this 1 over x times the polynomial here. If you don't like this written in its factored form with this weird 1 over x, you can always distribute the 1 over x and maybe write plus x minus 3 minus 4 over x. But there's not a lot we can do about this natural log of x times 2x minus 3. I'm not even sure what Wolfram alpha would try to tell you the answer to this problem is, or what the derivative of this function is. What do we have? X squared minus 3x minus 4 times natural log of x. Looks like Wolfram alpha multiplies that second term out. So you can see in, there it is. Oh, I can't highlight, there we go. You can see here that Wolfram alpha has decided to multiply that 1 over x over the x squared minus 3x minus 4. Any questions?
Yes, Professor Lich, you don't mind the very last line? How do you come up with the right x minus 3 minus 4 over x? How do
I
you?
used the distributive property. I took 1 over x and I multiplied it by the 4, 3x, and the x squared.
Oh, and then you, okay, thanks.
So it's questionable whether the second one is better or not. That will all depend on what you're going to be doing with this function. If the problem is to read this as the product rule and then apply the product rule properly, this first line is just as good. So Wolfram alpha So Wolfram alpha likes this one better, but does that mean it's really better? Also, now that I've dropped my opinion on whether, or questioning Wolfram alpha, whether it's better or not, what is Google and Facebook and all the other tech companies going to do with that information to target me with more ads? Any questions? Comments? Deep thoughts? So the natural log of x has some weirder behavior surrounding the chain rule, and it has to do with properties of logarithms and the way things work. Let's suppose we have a function h of x, and it's the natural log of 5x. This is very similar to our first problem. Our inside function is 5x. So u is 5x. That's bad grammar. U are 5x. Our outside function is natural log. So our y function is natural log of u. And we're going to need du dx. And du dx is 5. So a cool thing is going to happen with the natural log, the derivative of natural log of 5x. So h prime of x. The derivative of natural log of u is 1 over u. So derivative of natural log of 5x is 1 over 5x times the derivative of 5x, which is equal to 5. So this is interesting because the 5's cancel and the derivative of natural log of 5x is just equal to 1 over x. Sometimes we look at a result like this and don't even notice. We just accept that everything went fine and we walk away. We just go on to the next problem. But this might bother us that I changed the function that we started with. I changed from natural log of x to natural log of 5x, and I got the same derivative, 1 over x. Some of you might be bothered by this. So let's remind ourselves of some properties of logarithms. So we don't look at this and say these two different functions should not have the same derivative. If we remember our properties of logarithms, the natural log of a product is the sum of the natural logs of the factors. This is equal to the natural log of 5 plus the natural log of x. And so when we take the derivative of natural log of 5 plus natural log of x, the derivative of natural log of 5 is a constant. Or sorry, natural log of 5 is a constant, so the derivative is 0. So this natural log of 5 is constant. So the derivative is 0. So our properties of logarithms make this seem a lot less strange. So we're not worried about it anymore. It's okay that the natural log of 5x, or sorry, the derivative of the natural log of 5x is equal to the derivative of natural log of x, because the way logarithms work. Let's suppose that we look at a variation of this function. Suppose that h of x, capital H of x, is the natural log of x cubed. So the same thing is going on here. We have a chain rule problem where the inside is x cubed. That's been plugged into the outside function, which is the natural log of x, or the natural log of u. Oops, I've been calling this y. And since u is x to the third, we're going to need the derivative of the inside. Du dx will be 3x squared. So the derivative of natural log of x cubed is 1 over x cubed times the derivative of x cubed. If we simplify this, 2 of the factors of x cancel out. So we would just write this as 3x squared over x cubed, which is 3 over x. And once again, we might be thinking, how come when I cube the x, I only end up with 3 times the derivative of natural log of x? And once again, if we think about our properties of logarithms, the natural log of x cubed is equal to 3 times the natural log of x. So instead of the 3 being an exponent inside the logarithm, it's just a constant multiple outside the logarithm. So now I have a constant factor. So we have a constant times natural log of x. So the derivative of 3 natural log of x is just 3 times 1 over x.
Professor Leach?
Yes.
Question, please. On the property of logs. So you have ln x to the third power
Mhm.
equal 3n with the x. So in other words, you move the 3 to the front, isn't it? Is that how you do it?
Yeah, that's how the property works.
Okay, got it.
The exponent in the is the coefficients. This weekend, there's a couple of core derivatives that we're going to have to look up. So here are two important inverse trig functions whose derivatives we need to know. So arcsine and arctangent are inverse trig functions. Arcsine is the sine inverse. Sometimes this is written as sine to the -1, but it doesn't mean sine raised to the -1 power. It doesn't mean the reciprocal of sine, it means the inverse of sine, the function inverse of sine, not the multiplicative inverse of sine. Arctangent is the inverse tangent. So, in addition to all the practice that you're putting in finding derivatives, for Monday, I need you to find the derivative of arcsine and the derivative of arctangent, because those are the ones that we're going to put into the product rule, quotient rule, and chain rule on Monday. Any questions before we adjourn for the week? How's everybody, okay? Of course we're okay. I just went into wrap-up voice 10 minutes before the end of class, and it's a Thursday, which is effectively a Friday because I don't run classes on class meetings on Friday. It's just for office hours. All right. That's going to do it for today. That's going to do it for this week. Everybody have a good weekend. I'll see you on Monday, and thanks for playing.